Right. Next topic is binary addition, added circuits. So when you are adding two binary numbers, you will have a sum and a carry. Carry will be continued on to the next level. So let's say when you are adding two numbers, two binary numbers 0 and 0, sum will be 0 and carry is also 0. 0 1, sum is 1, carry is 0, 1 0 is 1 0, and when you have 1 1, the result is sum is 1 and carry is also 1. So this is not just an AND operation, sorry, it's not just an OR operation. Somewhere we have an additional term, carry is also coming into picture. Okay, I mean, just like when you are adding decimal numbers, what do you get? 8 plus 5 when you add, you will get 13. So you write the sum as 3 here and carry 1 will be sent to the next level. So here the result is 63. So like that, here also when you are adding two binary numbers, you get a sum as well as a carry. See, we have to develop a logic circuit for this operation. So one possibility is we can use a K-map table to solve this or simplify this expression if at all. Otherwise, here in this case the result is very simple. The sum is actually an OR operation. What about carry? Carry is an AND operation. The issue is, so when you are adding two numbers, the result is 1 0. Both are equal, sum is 0 and carry is 1. Okay. So ultimately, so this is an XOR operation and this is AND operation. Okay. So the result is, let's say you have A and B as inputs. Then this is the sum. This is the carry. The result is XOR. Adding 0 and 0, you get 0, 0 1 is 1, 1 0 is 1, 1 1, sum is 0 and carry is 1, it is 1 0. So if you are using two digits in the result, 0 0 result is 0 0, 0 1 0 1, 1 0 is 0 1. When you are adding 1 and 1, the result is 1 0. In decimal system, this result is 0, 1, 1, and this is 2. So next comes the case. So this is called half adder, because this performs only half of the addition operation. The major issue is if your binary number contains more than one digit. If your binary number contains more than one digit, like 2-3 digits, let's say 110, 010, trying to add them. What do you do? We'll add these two. Here it is 0. There is a carry. So this is also 0. This is the result. So what are you doing? You are adding two numbers. I mean, let's say this is A0, A1 and A2. And this will be B0, B1 and B2. So you are adding the A0 and B0, you get some result. If there is any carry, it will be forwarded as C1 to the next level, and you are adding A1, B1 and C1. You get the result sum, and you will also get a carry C2. Then you are adding A2, B2 and C2. You are getting a sum and also a carry. So at least you need to add 3 numbers. I mean, at most. Sometimes you may add only 2 numbers, but sometimes you may need to add 3 numbers to complete the binary operation, binary addition operation. So this performs only half of the activity. It adds only 2 numbers. But here, for the complete operation, we need to add sometimes 3 numbers also. I mean 3 digits needed to be added. So one is the number from the digit from the first number, the digit from the second number, and carry from the previous state. So all the 3 needed to be added. So to add to develop a circuit, or at least first of all the truth table, to add 3 binary numbers. So it is A, B, C with sum and carry. So we'll have 3 combinations. So I prefer to write in this sequence. It is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1. Okay, 0, 1, 0. Okay, so next one 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So in the first set, the carry is 0. We considered all the 4 combinations from the previous set, A and B. And in the second set, the carry is 1 always, and we have considered all 4 combinations for A and B. We got 4 combinations for A and B here, carry is 0. We got another 4 combinations for A and B with carry 1. Let us see the result of this. So when I add this, sum is 0, carry is 0, 1, 0, 1, 0, 0, 1. And here it is sum 1, carry 0. Here 2 digits, sum is 0, carry 1. Sum is 0, carry 1.
Sum.
Sum 1, carry 1. Just check the K-map table for this. So keep A here and B here. What is the K-map table? To fill so for 0 0 combination, your result 0. For 0 1, for A1 and B0, your result 0. For A0 and B1, your result 0, and for A1 B1, result 1. So this is A dot B. What about sum? So 0 0, result is 0, 0 1, result is 1, 1 0, result is 1, so 1 1, the result is 0. So you cannot make any combination from this. And here the result is A XOR B. When you have these cross terms, the result is A XOR B. The same way you have to prepare the K-map for this. What do you do? Either you can keep your C here and AB here. Any order is valid because order does not change the end result. You can take A here and BC here, whatever way is okay. Only thing is you have to carefully fill the table. So this is for sum, and this table is for carry. B and C is 0, sum is 0, A is equal to 1, is that okay? C, B, A, I mean, you can fill the table in the same order. So B is 0 0, 0 1, result is 1. 1 0, result is 1. 1 1, result is 0. Keeping C1, B as 0 0, result is 1. C1, DA is 1, result is 0. C1, B1, result is 0. So that is a complete table. So when you just have these cross terms, the result is XOR operation. It is A XOR B XOR C. Just like here. This is A XOR B. Here you have two cross terms. That is A XOR B XOR C. So what about the second table for carry? So for all zeros, the result is 0, 0, 1 0 is 0, 1 1 is 1. 1 0 0, it is 1. So C B A. 1 0 0, carry is 0. 1 0 1 is 1. 1 1 0 is 1. 1 1 1 is 1. So you cannot all you need is 3 terms. 3 combinations are needed. One is this, another is this, another is that. You need 3 combinations. So the first one C gets eliminated. You will be left with AB. The second case, B gets eliminated. You will be left with AC. Third case, AB. We take 3 inputs A, B, C. All the 3 can be used for XOR operation. And each combination, each pair will be given an AND gate AB, BC, yeah, so BC, AB plus BC plus AC. All the 3 combinations will lead to an OR gate, which is given. So we cannot keep C here, maybe because you are using C already here, keep a different notation on that. C out. So this is a full adder. So next one is IC parallel binary adder. IC parallel binary adder. The IC number is 74283. So it is a 4-bit binary adder. So this will have C0 as input, carry, let's say A0, A1, A2 and A3. So next one B0, B1, B2, B3. The result is sum 0, sum 1, sum 2, sum 3. So this is the first bit. So when you add A0 and B0 including C0, you will get sum 0 and carry 1. Carry 1 will go to the next level, so it will be added to A1 and B1. So here C1 is generated. After adding A0 and B0 with C0, we get sum 0 and carry 1. So carry 1 will be added to A1 and B1, we get sum 1 and carry 2. Okay, so then A2, B2 and C2 will give you sum 2 and carry 3. And when you add A3, B3 and C3, we will get sum 3 and carry 4. Carry 4 will come as output. And parallel operation, if your number has more than 4 digits, let's say 6 digits or 8 digits, you can place a similar IC here, 74283. So then the next series of digits will come here. So up to A3 it is over, A4, A5, A6 and A7. Next series is B4, B5, B6 and B7. We get sum 4, sum 5, sum 6 and sum 7. C8 as output. So if your number ends here, your C8 will be added at the end, and this is your total result including C8. If your number has only 4 digits including C4, this is your result. That is what I have seen here. Let's say 1101, 1011. Let's say when you are adding these two, 1 1 0 1 1 1 is 0 1 0 1. So you got 4 bits as some additional carry. So 4 sum bits and a carry bit. So this is C1, C2, C3, this is C4. So that is how we can perform parallel binary addition operations using that IC 7428. So this IC 74213 is designed to take 2 4-bit numbers as inputs and 1 carry as input, and it will generate 1 4-bit number as output and 1 carry. So when you are designing cascading adder circuits, I mean, if your given number has more than 4 digits, we may need to consider 2 ICs. So then the first IC will not have any carry input, and the second IC will take the input from the first IC. This C4 will be given as input to the second IC. This may be 0 or 1, but it will be connected to the output of the carry output of first IC will be connected as carry input for second IC. The calculation continues till all digits are processed in your given numbers. Okay. So if you are exclusively asked to draw parallel binary adder circuit, you can give a detailed description of this. Something like using full adders. Let's say full adder. This will have a carry input and 2 input bits A0 and B0. The result is sum 0. Output is C1. So it takes A0, B0 as inputs and C0 also as input, and it generates sum 0 and carry 1. S0, otherwise you can write it as sigma 0 and C1. So this carry will be forwarded to next full adder. Next full adder takes C1 as input, A1 and B1 as inputs, and it generates sigma 0 as output and C2 as output. Sorry, sigma 1 as output and C2 is also an output. So you can continue to any number of levels you want, let's say for 4 levels. A2 and B2, sigma 2, C3, A3 and B3, C4 is output and sigma 3 is the output. So this is the configuration of parallel binary adder. And if you are specifically using ICs, the IC number is 74283, which is a 4-bit binary adder. So the internal configuration of these ICs, this will have 4 full adders, so which which process each single bit individually.